This split-screen diagram compares the standard model of cosmology against a purely kinematic alternative. The top timeline shows the lambda CDM model, which requires three distinct mechanisms operating in isolated epochs: an inflaton field to force early expansion, dark matter to clump galaxies, and a late-time cosmological constant. This photograph of Adam Rees at Johns Hopkins University represents a major fracture in that standard timeline. His team's late universe distance ladder measurements differ significantly from early universe microwave background data. This discrepancy has surpassed a 5 sigma level of statistical certainty. While measurements of the expansion rate diverge, observational surveys are mapping structures that exceed theoretical limits. According to standard cosmology, matter should be evenly distributed at any scale beyond 1.2 billion light-years. This 3D star map isolates a formation called the Big Ring. Its diameter measures 1.3 billion light-years. The existence of a structure this massive violates the cosmological principle of homogeneity. Maintaining the current framework requires patching these observational gaps with independent, unproven entities, specifically the inflaton field and dark energy. These recurring anomalies suggest the need for a unified foundational mechanism. Andrei Sakharov proposed a different starting point, treating spacetime as an active, elastic membrane. In his induced gravity program, the properties of space emerge from the vacuum's physical resistance to being stretched. The concrete arms of the LIGO detector, shown here, rely on that elasticity to function. When gravitational waves pass through the Earth, they physically stretch and compress the local spatial membrane at the speed of light. Physicist Boris Kriger has developed a model where cosmic expansion is driven entirely by the centrifugal relaxation of this spinning membrane. Unlike the standard model, this approach requires zero free parameters to predict the history of the universe. If this mechanical interpretation is accurate, the exact expansion rate of the universe and the Big Ring size can be derived using only classical angular momentum and measured constraints from nuclear physics. The model begins with the universe at its absolute limit of density. It sits at a radius of exactly 15 astronomical units, capped by the physical limits of nuclear matter. Kurt Gödel previously attempted to model a rotating universe, but he used standard three-dimensional space, spinning around a single axis. This approach created unphysical results, such as paths that loop backward through time. Kriger's model avoids this by defining the universe's topology as real projective 3 space in 4 dimensions. Rotation on a 4-dimensional spherical manifold operates differently than in 3D. Rather than spinning around a single central axis, the rotation decomposes into 2 independent orthogonal planes. If the membrane undergoes isoclinic Clifford rotation, rotating at equal rates in opposite directions across both planes simultaneously, the total angular momentum of the system cancels out to exactly 0. Because this double rotation covers all 4 directions in the ambient space, the resulting centrifugal force acts isotropically. It pushes the membrane outward equally in every direction. This topological constraint explains why the expansion appears uniform. It allows the universe to act as a centrifugal engine, while ensuring the cosmic microwave background shows no global spin. This chart illustrates the model's kinematic constraint, the 4-velocity budget. The total available velocity is the speed of light. In the initial 15 AU state, the rotation velocity consumes the entire budget. With rotation maxed out at c, the velocity of time is 0. As the centrifugal force pushes the membrane outward, the radius of the universe grows. To maintain stability, the angular momentum of this mass must be conserved. This conservation requires rotation to slow as the radius increases. As the rotation velocity drops, the unused portion of the velocity budget becomes available. This leftover velocity is what allows the membrane to physically expand. By integrating this centrifugal acceleration, we find that the expansion velocity of the membrane squared must equal the speed of light squared minus the rotation velocity squared. This derivation yields a direct identity. R dot equals v time. The rate at which the universe grows is the same physical quantity as the speed at which time flows. Time is not an independent dimension that ticks away in the background. The passage of time is literally the freed kinematic budget resulting from the physical deceleration of the rotating universe. This framework replaces the need for dark energy. Instead, the cosmological constant is calculated from the shift of the chiral condensate inside a nucleon, a value derived entirely from nuclear physics. Applying that nuclear-derived constant to the expansion equations yields a predicted Hubble parameter of exactly 71.7 kilometers per second per megaparsec. This maps the current Hubble tension. On the left, the early universe Planck measurement stands at 67.4. On the right, the late universe SHOES measurement sits at 73.0. The theoretical value of 71.7 lands precisely between these two conflicting measurements. The model suggests that both experiments are observing a screened version of the expansion. We measure the recession of distant galaxies, which are trapped in the dense cosmic web. That web physically resists the expansion of the underlying membrane, causing measurements to deviate from the true rate. This image of the James Webb Space Telescope anchors a crucial observation. Recent deep field surveys detected an excess of galaxies rotating with a specific handedness. That spin asymmetry is a direct physical signature of an underlying rotating medium. The Hubble tension vanishes when we filter the data through a single continuous expansion rate, rather than assuming a non-rotating universe. If the universe is built on a four-dimensional rotating topology, that geometry should be visible in the physical layout of galaxies. This animation displays the Hopf fibration, decomposing a spherical space into a continuous family of nested, interlocking tori. As the universe expands, this vibration acts as scaffolding, dictating pathways where matter must cluster to form large-scale filaments of the cosmic web. By calculating the baryon fraction over this geometry, the math predicts that massive concentrations of matter will gather at a specific angle, roughly 2.8 degrees from the polar axis. Mapping the geometric cross-section of a torus at that angle yields a physical diameter of precisely 1.35 billion light-years. The big ring represents a visible 1.3 billion light-year cross-section of a topological Hopf torus. Its dimensions are a direct consequence of the universe's shape, predicted with zero free parameters. The centrifugal model replaces the inflaton field and dark energy with the physics of rotational momentum. In this framework, expansion, the passage of time, and the layout of megastructures are all different expressions of a single mechanism, centrifugal relaxation. This topology makes a specific, testable prediction. Every massive structure must have an antipodal mirror-reflected image on the opposite side of the sky. This is the Sloan Digital Sky Survey Telescope. To verify this model, researchers must search its deep sky maps for a mirror-reflected version of the giant arc formation, located on the opposite side of the celestial sphere. Solving these cosmological anomalies requires a better understanding of the shape and the spin of the membrane we live on.